So I'll be talking about a general distributed framework for the contraction of a sparse tensor with a tensor network. So acceleration of sparse tensor algebra has been traditionally pursued by runtime libraries like CTF, TC, DANSOM, which is a recently proposed runtime library. And then code generation, which the compilers are pursuing, like TACO, Comet, Sparse Distal, which is built on top of TACO. And also through specialized hardware. Some of the examples are Xtensor that we have been listening to this in the talk. So these prior works have been mainly focusing on efficient contraction of two sparse tensors or two dense tensors or a general contraction of any number of tensors. But there's also a huge body of literature where specialized kernels like MTTKRP, TTMC, STDMM are pursued to be accelerated. There are specialized libraries that are available like SPLAT, Part A, ADTM, which accelerate only specialized kernels like MTTKRP and so on and so forth. So why are we trying to like optimize or accelerate these specific kernels? Because in tensor decomposition or completion, the optimization methods generally leverage either all or parts of the residual error norm, which means that this particular equation finally leads to contraction of a sparse tensor with many dense tensors. So there is a sparse tensor that is being contracted with a lot of dense tensors. Similarly, for tensor completion, which is of importance, the main bottleneck or the kernel is the contraction of a sparse tensor with a tensor network. What about the output? The output is either a small dense tensor of comparable size or a sparse tensor which has the same output sparsity as the input sparse tensor. So we refer to these as SpTTN kernels, where the contraction of a very large sparse tensor is contracted, which generally represents an input data set, with dense tensors, which represents the factor matrices, and the output is the dense tensor. So as I mentioned, there's a lot of work that has already been gone into like building specialized libraries for targeting one of these kernels. Like there is a kernel, if I take MTTKRP, there is a specialized implementation for MTTKRP alone, both on shared memory and GPU. But what in this work that we are trying to do is generalize the state-of-the-art implementation. So can I just write any SpTTN kernel, and can I get the same performance as a specialized code rather than taking the generalized approach? So this is what we present. So we have a SpTTN Cyclops kernel or framework, which given any SpTTN kernel, which means that any sparse tensor contracted with a network of dense tensors, we are able to accelerate and show the performance. But how do I actually compute an SpTTN kernel? So there are approaches, like if I take TACO, I believe that the default code just generates a series of for loops. For this is an example of a TTMC kernel, where the TACO would generate a series of for loops. But runtime libraries like CTF do a pairwise approach, which means that they contract two tensors, get the output tensor, and then contract the output tensor with the remaining tensor. But the disadvantage of this approach is that the intermediate tensor is a dense tensor and pretty huge because the ij indices are pretty huge, right? So there have been recent works which try to from the compiler perspective, both Sparse LNR and React. Sparse LNR is built on top of TACO, and React is built on top of Comet, which try to fuse these loops. So what they do is they identify that I can have the same j and I loop going around for both the contractions, and so that I don't have to actually store the I and jth index, which means that my now intermediate tensor buffer size is limited. So this is what the compiler is doing. But the one thing that to note here is that this is not a unique loop structure, because I can see this tree and say that if I had not iterated over k and s in the first contraction, but had iterated over s and k, my buffer dimension would not be a vector, but just a scalar value, right? So the goal that we are trying to achieve in this particular framework is, given any contraction of SpTTN structure, we have to find the optimal contraction path, and for any given optimal contraction path, we want to fill up those indices such that I can minimize either the intermediate tensor dimension, or I might want to minimize the number of cache misses, or I might want to minimize the number of strided accesses, so on and so forth. So this is the framework overview. So what we give is, the user just inputs an einsum. It can be either through Python or C++. And we distribute the tensor because it's a distributed tensor framework, and we keep the input tensor in its place, and we distribute the output tensor such that the matching indices are replicated. And then we find an optimal contraction path such that the asymptotic complexity is the minimum, And then for the contraction path, we try out different loop indices. So here you can see that it has figured out that there are two loop structures which can generate two different code structures. The first loop structure is giving rise to an intermediate tensor of vector, but whereas the second loop structure is giving rise to an intermediate tensor of scalar value. So it tries to pick an intermediate tensor dimension of the least quantity if that is what the user provides. So the user can specify this is what I want to minimize on, and then it generates the code. Here, when I say generates the code, I am not talking about the compiler because this is a runtime system. So we heavily use metaprogramming to generate this code, which means that we have a lot of hash diff statements. And then once the code is generated, we offload it to BLAS kernels. So BLAS 1 and BLAS 2. So even though it's a sparse kernel, there are inner loops which are dense, so which I can offload it to a BLAS call. So we are able to match the performance of a specialized library because we are able to generate code such that we can minimize on any of these particular function. So we present an algorithm which can actually generate the entire space, and then optimize it over the loop space. So we enumerate only loop nests that are optimal in computational cost, which means that we pick a contraction path. Again, this is with a caveat because I might choose to pick something which is higher computationally intensive because maybe I don't want to transpose the tensor, so that is also built into the model. And then once I pick an optimal contraction path, if I just enumerate all the loop nests that are there, then the complexity is m factorial power n. I'll not go into the details, but what we do is we use an approach from dynamic programming, and we try to we build an algorithm which can prune the search space, and we use memoization. And this can be plugged in by a cost model. The cost model can say, I want to minimize the intermediate tensor dimension, I want to minimize the number of cache misses, or I want to increase the number of BLAS calls that I can have. So if I look into this particular thing, even though it says the second one is optimal because the intermediate tensor dimension is just 1, I might want to still have a higher intermediate tensor dimension because it can give rise to higher number of BLAS calls. So this is built into the system. And then we see that the complexity, we derive the complexity is upper bounded by 2 power m n factor n power 3 into m. Even though it's higher, we are able to run this for many of the kernels that we have seen in less than a second. So we are able to pick an optimal contraction path in less than a second, optimal loop nest. So given a structure like this, the code generates the for loops on the runtime, not making, of course, the compiler itself generates, but it's not like the compiler has to be compiled. Right? So it's just generating the code on the fly, and then it also identifies the BLAS calls and offloads it. So if I have to execute this TTMC order 4 kernel, then it figures out that this is the optimal loop nest for some cost, and then it says, okay, I want to offload these particular inner loop structures to BLAS calls, and maybe some of the loops that are dense, maybe I want to just generate it using metaprogramming or C++ templates. We ran this on the Stampede 2 supercomputer, and we see that the single node performance, we compare it with Sparse LNR and TACO and CTF, which is the default, which is what CTF, this framework is built on. And SPLAT is a library which is heavily tuned only for MTTKRP and TTMC, so we compare it for MTTKRP. And we see that we match the performance of SPLAT, which is again hand-tuned for MTTKRP kernel, and we outperform both Sparse LNR and TACO. And for distributed, we scale in similar lines to SPLAT, which is a hand-tuned library. And for TTMC, we are able to run some of the kernels which the TACO and Sparse LNR we were not able to execute on. And we see huge speed-ups just because it's able to pick an optimal contraction path and a loop index order. And for TTTP, which is an output tensor, which is sparse, we are able to generate the code, and we are able to outbit the CTF, which is the only one which handles output sparsity currently. And then for the TTCC, which is a fairly complex kernel, which has order 6 kernel, so we are able to execute it, and we are able to scale efficiently. We were not able to run the TACO or Sparse LNR on this kernel for this particular size or sparsity. The conclusion is that the implementation of high-performance SpTTN kernels, which is of very high importance or interest for both tensor decomposition and completion, can be automated. And we can search the entire space in less than a few seconds. And we are able to pick an optimal loop nest for this, and we are able to execute it. And we are also able to offload it to BLAST kernels. So the future, one of the works that we are now exploring is, instead of the BLAST 1, BLAST 2 kernels of the CPU, can we offload it to a GPU's cuBLAST kernels so that it's handled for us, right? So that's one of the approaches that we are taking. We also have some sophisticated cost models like cache misses, which we haven't yet tried, so we are trying to build into this particular model. So yeah, this concludes my talk. Thank you.